In our last film, we investigated a new puzzle regarding the expansion rate of the universe. We interviewed a number of scientists, including Adam Rees, who won the Nobel Prize for discovering that the universe is accelerating in its expansion. The accelerated expansion is said to be driven by a mysterious dark energy. Some physicists claim the nature of this dark energy is the biggest problem in physics, because its value seems delicately fine-tuned and unnatural. But one of the founders of loop quantum gravity, Carlo Rovelli, explained to us why he disagrees.
Here's the question: is dark energy is the biggest problem in physics? No, not at all. I think that the big fuss about dark energy is wrong, is based on misunderstanding. It's just a way to sell and ask for money in grants, but it's a badly exaggerated problem. And I think there's a lot of confusion about that. So let's put things straight the way I understand them. First of all, there is good evidence that the universe is accelerating, the expansion of the universe is accelerating, and there is a very clean theoretical model that is compatible with this and predicts it with general relativity as it was written by Albert Einstein in 1917 in a paper in which he introduced the cosmological constant. It works well, it's correct, it predicts the accelerated expansion. Where is the problem? Okay, so why do people go around saying, oh, there's a huge problem in physics? For a number of reasons, all of which are confused, in my opinion. The first reason is that people remember that Einstein was unhappy about that. So Einstein wrote, according to Gamow, Einstein said, that was a mistake of mine. But the mistake of him was not introducing the cosmological constant, was that he introduced the cosmological constant because he thought mistakenly that with the cosmological constant, the theory could be compatible with a static universe, no expansion whatsoever. And since he was mistakenly believing that the universe was not expanding at the time, because before Hubble, he added the constant trying to correct his theory to agree with the wrong expectation he had about the universe. So he was 3 times wrong in this, and what he should have done is to realize that with or without cosmological constant, the theory predicts expansion, and he would have deserved one more Nobel Prize if he did so, and he missed the prediction. So that is why he was unhappy with itself. There's nothing wrong with the cosmological constant. In fact, a cosmological constant had to be there. There's no reason for it not to be there. It's one of the constants of general relativity. First point. Second point, which is more important, particle physicists thought that the cosmological constant is just the quantum vacuum energy and nothing else. That's a totally mistaken idea. It's like saying that the charge of the electron is just the radiative corrections to QED. But that's a confusion. I mean, the electron has a charge, and to the charge you add the radiative corrections to QED. The quantum fluctuation of the vacuum are a teeny correction, or a correction to the energy of the electron. So there's a cosmological constant, which is a constant to the theory, and then there is a renormalization, the quantum fluctuation that correct it. The idea that the cosmological constant is the vacuum fluctuation is just wrong, physically wrong. Cosmological constant is a constant in the theory, and then there's a quantum field theory that corrects it. Third point, the corrections to the cosmological constant in quantum field theory are huge, and people say, wow, mystery. This cosmological constant is teeny, and these are huge. But what's the issue? That's all the constant in quantum field theory. That's true for the mass of the Higgs, That's true for the charge of the electron. That's true for all the 19 coupling constants of the Standard Model. The mass of the Higgs and the cosmological constant are sort of bigger because go as the power of the cutoff instead of logarithm, but still, I mean, they're all infinite. So there's no reason for the cosmological constant to be more of a problem than the mass of the Higgs, which also is a problem because you have to take away this infinity. But this taking away this infinity is what we do routinely with the Standard Model. So if you say in the standard in quantum field theory as we do it, there's a problem with these infinities we have to normalize, okay, fine. But it's not the cosmological constant, all of them. If you say, oh, that's not a problem for the cosmological constant either. You see, what has happened is a lot of misunderstanding one after the other. Einstein adding the cosmological constant hoping to stop the universe from expanding, and it's not true. The particle physicist is saying, oh, we know what is the cosmological constant is the vacuum fluctuation. Since that's not true. Then there was this story with string theory. String theory is compatible with a negative cosmological constant, but not a positive cosmological constant. At least for a long time, people believed that it would not be. So when the astronomers observed the faraway supernova to indicate that there is an accelerated expansion, the string theory community didn't believe that. And for many years, you would hear at string conferences, oh, the astronomers say that, but they will change their mind because better measurement will, because we know better that there could be no positive cosmological constants. But nowadays it's pretty solid, the evidence for the accelerated expansion. So the string theory had to say, all right, so let's rethink, maybe we can readjust string theory to a positive cosmological constant. So the cosmological constant has been disturbing all the time with sequence of misunderstanding. The present situation is that in fundamental physics, the world seems to be very well described by the Standard Model and generativity with two constants, the Newton constant and the cosmological constants. We know the values of all of them, measured, and all of them have to get renormalized by quantum field theory, but what we measure is a renormalized quantity, not the bare quantity, so there always is this infinity to deal with. That's the situation it is. There's nothing that makes the cosmological constant special in that. Having said so, obviously it's good to study alternative. Maybe the accelerated expansion is to be described by a different model than generativity with the cosmological constant, fine. It's good to make more precise measurement. It's good to study alternatives, that's what physicists do all the time. But to say there is a major mystery in fundamental physics, in my opinion, is bullshit. Two more comments. One is that people say, yeah, but this constant is so small compared to the others. After all, the others are all more or less in the same range once you fix appropriate units. This is unnaturally small or large, depending how you write 1 over it. True, but so what? Who said that there should be no small numbers in the fundamental description we have of the world? And I want to remember one thing, that the idea that there could be not large numbers or small thing, or small numbers in physics has mistaken us already several times in the future. There are at least two famous examples. One is heliocentrism, the idea that the Earth goes around the Sun, which, as everybody knows, was proposed in antiquity by Aristarchus. So Aristarchus said, well, the Earth rotates in itself, that's a day, and the Earth goes around the Sun, that's a year. great idea. In fact, correct. And it was discarded. And why was it discarded? Because if the Earth goes around the Sun, and you have a star far away, since you move, and it's very large, the orbit of the Earth, you would see the star doing that during the year. But we don't see the star moving. Of course, there's one possibility that that star is very far away. So we know that from Archimedes. In antiquity, it was understood that since we don't see this, it's called the parallax. Since we don't see the parallax of the stars, we don't see the stars doing that, either the Earth does not go around the Sun, or the star has to be far away. But very, very, very far away. There's an enormous number there. And people said, oh, that's not natural, that they're so big. The universe cannot be so big. It would be unnatural to think that there is such a great number out there. So they discarded that, and they were wrong. And again, when atomic theory was much discussed in the 19th century and toward the end of the 19th century, many physicists, very good physicists, did not believe in atomic theory. The chemists were using atoms, but the physicists didn't believe that there were these tiny things which are molecules and atoms. So there was a minority that believed in Maxwell, Boltzmann, of course, they were atomists. But the majority of the theoreticians in physics took atoms for a theoretical idea that would not correspond to... And one of the arguments was, come on, if atoms were real, they would be too small. And things cannot be too small, unnaturally small, right? So, of course, there are small things and large things, right? When we look far away, we test physics that go around our common... that's one point. There's nothing unnatural in having a small number in the fundamental Lagrangian. It's a normalized observed quantities. The second point I want to make is about fine-tuning. There is a lot of talk about fine-tuning today, which, once again, I think is wrong. Very often, fine-tuning arguments are wrong. In renormalization theory, you always fine-tune. Namely, the way we do quantum field theory is by assuming that there's a cancellation between the bare value of constants and the radiative corrections, which cancel one another. And this is always a fine-tuning. And it's very, very fine for a cosmological constant, but it's a general issue. And it's because we don't understand quantum field theory non-perturbatively. It's nothing to do with physics. It has to do with our bad control of a mathematical theory. The other argument that people give for fine-tuning is, and we find it all over, people say, look, the constants of the universe are very fine-tuned so that the universe is complex, there is chemistry, there is life, there is us, and so on and so forth. And this seems mysterious. And I think the logic is upside down. I mean, look, the universe, the history of my mother and father and grandmother and grandfather is so very fine-tuned so that I came out. My father went to that particular restaurant exactly the same day that my mother went to that restaurant. And if he had gone one day after, one day before, they wouldn't meet, so I wouldn't. So the universe is fine-tuned for me. No. I mean, the universe is what it is. I came out, right? If my father had gone one day before, instead of meeting my mother, he would have met somebody else. So instead of me, there would be some other person. So life and chemistry are fine-tuned to whatever the value of the constants are, not the other way around. It's the result which is a consequence of the constant, not the constants which are fine-tuned to the result. And people say, yes, but if the constants were a little bit different, there would be nothing. And that's incredible intellectual arrogance and stupidity, because nobody would be able today, from the Standard Model, to predict chemistry and life. Nobody at all. So how do you know what would happen if you change a value of of a constant? Imagine you change the mass of a quark, a coupling of the Higgs a little bit. Of course there would not be carbon, there would not be stars, but there would be something else. And nobody's able to say correctly and plausibly and credibly that the universe would not be complex and whatever, because we're not able to do these calculations. The universe is strongly non-perturbative. I mean, quantum dynamics is strongly non-perturbative. Chemistry. So we know that with these values of the constant, that's the universe that comes out. We have no idea what would happen without the value of the constant. And the argument, oh, but if I change that, there will be no stars, no life. So what? It's like if my father hadn't met my mother, there would be no Carlo. But so what? There would be Paolo or somebody else. So I think that arguments about fine-tunings are just wrong logic. Argument about naturalness, naive argument about naturalness are dangerous because they make us miss important physics. And the cosmological constant is no less strange in its behavior than all the other constants in quantum field theory. So the idea that the cosmological constant by itself is the greatest current mystery is profoundly wrong. And why I say that? Because I think that orienting research in that direction is a waste of time. There are better things to do.
Okay. There's one thought I have actually, which is, and I think you kind of said it, but I don't know. People say it's a fact that these constants are fine-tuned, and one suggestion for why there might be is there's a multiverse, lots of different universes, maybe there isn't. There's one that you can't test that. So that I don't like that solution to this problem. And I've always thought, but you can't test the problem. Like, you can't do an experiment where you change the constants of nature and then confirm that you're right, that there can't be life. So it kind of goes both ways. Like, okay, if that solution is no good for you because it can't be tested, then the problem shouldn't be any good for you.
Oh, very good. That's very good. That's very good. I agree fully. We cannot test the idea that changing the fundamental parameters you don't have life. And we can neither test it empirically, we cannot just move them and try different units, nor even test theoretically and compute it. So I fully agree.